Okay, so now we're going to be talking about computational thinking. So whereas in the previous section, I introduced two ways that you could potentially express your algorithms, right? In pseudocode, just writing it out step by step, and pictorially in a flowchart. Depending upon which one you use, it's like it's how what helps you think through a problem. So what I would like to take you through now is just like I want to go through some problems with you so I could start giving you tools to actually turn, the problems into algorithms, into those step-by-step guides that you need to do in order to solve your problems. So what is computational thinking, right? So we start out with a problem specification. So when someone asks you to solve a particular problem, the first thing you really need to do is you need to break out what that problem is. So the first step is that decomposition, breaking it down into its simpler parts so you really understand exactly what the problem is. Make sure that you have a precise understanding for all the criteria that you're going to need for a solution. The next step is pattern recognition, right? And that's where you can look to see if the problem that you're trying to solve already exists in either a previous problem that are known and that are common, or else something that you yourself has solved before and can really take that problem or take a piece of the bigger problem and compare it to something that you already know and just modify what you already have or use exactly what you already have in order to solve the current problem. And then the last piece is like, right, abstraction, where you're sometimes that abstraction could be done by getting rid of some of details that you don't necessarily need to deal with to begin with in order to solve the problem. So it's almost like, simplifying down the problem to a more abstract version of it. And then once you have a good understanding of that version of it, then you can, bring in the other complications afterwards. And then, algorithmic design. So that's that step-by-step solution. And then, right, so once you have that, then you want to go through the phase, which we're not really going to be talking about here, of the implementation and evaluation, because that's where you're actually putting it into code and testing it. But that certainly is the last piece of it. You could do that a little bit, if certainly if it, deals with numbers. If you want to see if your concept works, then you try it out with you put in some input of numbers and you make sure that the flow of your algorithm, it actually makes sense and works. So just to break out those pieces, right, the problem specification. So with decomposition, right, so what are you doing? What you want to do is, right, you want to break it down to all the different operations that you need to do and if there are constraints that you would have to put on it, right? So you want to, and the best way to do it is actually to write these things down, right? I don't care if you do it, electronically and you type it down or actually take a pen and paper and you write it down. So you want to break that problem down into the different operations that you have to do and into what the constraints are. For example, we saw before, right? So when you're asking them to even the simple question of, like the birth date, right? So the two operations that you would have to do there is you'd have to find out what today's date is and find out what your friend's birthday is. And a constraint might be that you want to make sure that the format of the two dates are in the same format, right? So in America, we refer to a date as, the month, the date, and then the year. And in European countries, they actually put the day and then the month, which could get very confusing when you're trying to compare it. So that could potentially be one of your constraints. So you need to make sure that all of those things are defined ahead of time and very clear up front. It will also help you, understand how to abstract something potentially, because if you had all of everything written out, then you could say, well, I could take a simpler version of it and remove that out of it. Okay, so that's the decomposition piece. The other pieces are the pattern recognition, right? So that's looking to see if there are, analogies for the problem that you're trying to solve, right? Have you already solved it, or is there already an algorithm out there where someone else has exactly solved either, your exact problem or something very similar to the problem? And then the last piece is that abstraction, right? You're looking for a reduced version of what you're trying to solve in order to be able to focus on, solving the problem first and then being able to bring in other complications, right? So if you understand that essence of what your problem is, then you can start adding other, specifications on top of that. Okay, then once you have yours, right, it's only then when you try and bring in, right? So once you have that, that problem specification, that's when you would start programming into a programming language like Python or Java or C++ and all the rest. And the reason why you don't want to do that to begin with is you have to separate the two, because when you're translating it into the specific programming language, that's when you have to worry about the syntax of the programming language. But if you don't have the problem thought out properly, then you're going to be focusing on, well, how do I code this, rather than am I solving the problem that I need to solve? And then once you know that you're solving the problem you need to solve, then you could worry about the syntax that you're going to be used to actually write the program. Okay, so let's start with a simple algorithm, right? So what are the steps to perform long addition on two natural numbers? And remember, I know now you put it into a calculator, you put it into a computer, but just to like work through in your brain what you would need to do, right? Let's say you have 342 and you want to add, I don't know, 3,453, and I'm not going to remember what those numbers are. But if you go back to, I don't know if it's third, fourth grade math, right? So what are the steps that you would have to do in order to solve this if you're going to do it according to long addition, right? So you line the numbers up vertically by place value. So there's the ones place value, the tens place value, the hundreds place value, and so on and so forth. You start adding with the smallest place value first, right? And then, right, this is the regroup. This would be like your decision base, right? So if the answer in a column has two digits, right? So if 3 plus 7 is going to give you back a two-digit number, so then you have to, we used to call it carrying it over, but you need to be able to move it over to the next column, and then you repeat this for each column. Right? So we're seeing both a sequence, right? First, you have to line them up and start with adding the smallest place value. This is going to be a decision, and this is going to be a loop, right? So if you think about how you would actually, write this out as code, it's not going to be so simple, right? Because you'd have to actually break it down into all those pieces. And so, to abstract this, you could say, well, let's just start with, single digits, right? If I'm adding just 5 and 9, right? So then when you bring it over, so then you don't have to like worry about that 10 places. And then you could go to the next level and make sure that you understand all those implications. But I think you can start to see what I'm saying by breaking this down into pieces so that, you can do it in a step-by-step process. A little bit harder, right, would be sorting. So there's, just so you know, there's many different algorithms out there for sorting. This is called a selection sort. And the idea behind the selection sort is it repeatedly finds that smallest value in the unsorted portion and moves it to the front. Okay, so right, so if you have like a whole bunch of numbers and you have your initially, your 0th position is whatever, and everything is all the smallest, a mixture of unsorted numbers. So if you find the smallest number, you put it in position 0. Then you find the next smallest number, you put it in position 1. Then you find the next smallest one and put it in position 2, and so forth, so on and so forth. That is the algorithm of what this is supposedly taking you to. So here you set the minimum to location 0, right? So you're your minimum one is going to be location 0. Then you find the smallest element in the rest of the list, and you replace the value at the location min, right, with a different value. And then you increase that min position from location 0 now to location 1, and you repeat until this whole list is sorted. Okay, so this is that step-by-step worked out. I want to show you what that would look at in a little bit more advanced pseudocode. And this is where you're having a concept of a for loop, meaning this is, right, so this is, that list is sorted. So you, right, if you remember back to our different ways of how you might process something, that sometimes you're going to go in a loop. This for loop is one way of representing a loop. So you're saying for each number I, right? So you're setting, so the I is going to start out at 0, right? So the smallest number starts as 0, right? And then you're having another for loop where you're going to have to actually go through the list and then move that back to the first number and then swap the number in the smallest number. So what this ON2 is, n squared equal to, so I'm going to be talking about that a little bit. This is something, it's a concept I'm going to introduce. You're going to be learning more about this, not necessarily in the first semester, but we're going to really be more addressing this in the second semester, right? So one big thing that you have to be aware of when you're writing algorithms is that it needs to be efficient, right? So if you're dealing with just a small group of numbers, then it doesn't necessarily matter how efficient it is because it will end very briefly. But you could imagine if you're dealing with, you know, sales figures, or if you're dealing with genetics and you're dealing with millions of numbers or millions of calculations that you're doing, that's when that small fraction of a second is really going to be important. So there's a concept called the big O notation, which tells you approximate how much time it's going to take. And what it does is it calculates the number of operations that you would need to do in order to accomplish your task, right? So here's a list of some of the operations, right? Addition, subtraction, comparison. So each one of those is a separate operation, and each one of those gets counted. So if you have, let's say, you know, 100 pieces of data, O to the n means that there are 100 calculations, right? O to the n squared would be 100 squared. So that's 10,000. So 10,000 in and of itself is not so bad, but very likely you're not going to be dealing with it in 100. You're going to be dealing with something much larger than 100. So a sort like this, where it's ON squared, as long as your list is fairly short, that's a fine way of doing a sort. But once you get to a list that's much longer than that, then you have to start looking into much more efficient algorithms. But for right now, I just want you to like think through, like if you were given, you know, a whole list of papers or even a whole bunch of cards, right? And you know, a really big stack, like 1,000 cards. One thing you might want to think through just on your own is how you would go about sorting that stack of cards. Okay. I'm going to introduce this, and I'm going to tell you that there are algorithms out there to solve this. But if you want if you want to start playing with this on your own, you're welcome to do that too. This is called the traveling salesperson problem, and it is not a new problem. The idea is how do you go from point A to point B, right? From start to end in the shortest path. So what you see here is in between, there are 4, these are nodes. This is called a graph, and each of these lines is called an edge. And the number that's associated with this edge is a weight. So the idea is how to calculate the shortest path, meaning the path that has the least weight to get from start to end. Now, this is a fairly small graph, so you could just do this, you know, by hand, and you could figure out all the possible paths to get from one to the other, and then, you know, figure it out that way. But you can imagine if this truly was, you know, imagine there was, you know, a person even just visiting like I don't know, 100 different cities in the United States, and they had to do some problem like this, and they wanted to get from one to the other. So it's one mention is called Dijkstra's algorithm, which you don't have to worry about it yet. But the idea is that there are many problems out there. Algorithms have already been solved for them. And then sometimes it's dependent upon, exactly how close what you're trying to solve is to an algorithm that's already out there that you could potentially use. I want to go through one more example with you. And this is I'm just trying to give you some tricks, some ways to think about things, some ways to break things down so that when you yourself are given problems, when you're going to be starting to be coding, you can start applying some of these techniques to your own problem solving situations. Okay. So this one last thing I'm giving you is the need is you want to store a bunch of images on a flash drive. And then some of those specifics or some of those constraints, right, are different kinds of images, right? You might have different kind, a JPEG image, a GIF image, right? And you have different sizes of drives. So your flash drive might be, a 2 terabyte flash drive, or it might be a 1 gigabyte flash drive, whatever it might be, right? So let's break this down. So what's my problem description? I want to calculate how many pictures can fit on a drive. And the requirement is that you have to develop some computational solution to determine how many images can fit on the given size drive. So let's look at some of the specifications, right? The drive size would have to be entered. And we're saying, we're defining that it has to be entered in gigabytes, right? And then the number of images that can be stored has to be calculated for a GIF, for JPEG, for PNG, for TIFF, and any other file formats that might be out there. And then the type of information that you could potentially give back is, the size of the drive can handle this number, this number of GIF, this number of JPEG, and so on and so forth. So let's look at what are the facts that we know, right? The size of a given image depends both on the image format used and the image itself, right? And some formats, like JPEG, allows the user to select a degree of compression, meaning that the actual image might take up a certain number of bytes, but it could be compressed to take up less space. So for starters, what you want to do is you want to start with some assumptions. So let's start with the assumption that all images have a resolution of 800 by 600 pixels. Okay, it's great to give yourself some upfront assumption. And then, like I said, once you have it worked out for a simple situation, then you can start allowing for numerous different options. And what you're saying, another assumption you're making is that the compression ratio is 25:1. So if we have a 16-bit or a 2-byte color depth, right? And we have our 800 by 600, so then the 800 by 600 by 2 depths would be a total of 960,000 bytes. And then the compression ratio is 25:1, which means in order to understand how many bytes it would take to store this, we could divide our total number by 25 and come up with this number. Now, this is a lot of, I know I'm getting into very specific details with you about this, but what I'm trying to show you here is that you can come up with some assumptions that very much simplify what the bigger problem is. Because then once you have those assumptions, right, now we can go about solving the problems, right? So what have we done in order to solve the problems? We're ignoring, right, for our first assumption, we're ignoring other details. So we're using, divide and conquer, or whatever, it's not so important. But, for starters, we're saying we're computing it just for GIF. So we're computing it just for JPEG. So we're coming up with some assumptions to make sure that we can get our handle on the problem, solving it for that, and then relaxing those assumptions as we want, right? So we're coming up, right? So we have our data representation. And then here, right, so if our USB could be 300 bytes, and we're saying that one image takes up 30 bytes, so then it's very easy to do that calculation and figure out what the end result will be, right? So find our algorithm. So our algorithm would be that the total number of files that we can hold on our disk or on our total number of files that can be stored is, right, so our size of the USB, so that's our 300, times one image over the size of one GIF, which means that we're going to be multiplying that by 1 over 30. And that's going to tell us that we can store exactly 10 images on our file. And this is just like formulating it a little bit more, right? So you're going to prompt the user for the USB drive. You're going to calculate the size of one GIF, and then you're going to use some predetermined calculation in order to be able to come up with our number of files that we can store in the end. So I think this is just right, wrapping it up. You determine what the specifications are, and then you create the design in order to implement that, and then you can actually implement that design. And that last step, like I said, is going to be putting it into computer language. And then, so what I'm right, so you're going to define your algorithm for a small piece, and you're going to actually taking it all the way through. You're going to create it, and you're going to implement it in code, make sure that you see it working, and then go back and adjust your algorithm to additional specifications. So in the case of the images on a particular file, right? So then you could relax your constraints based upon the resolution, based upon the color depth, based upon the compression ratio, based upon the image type. And then, right, so, but you have a basis, you have some small abstract version of your total problem that you're working with. Okay, so it's a very good tool to use to create that small version first and then go beyond that. So understand what the problem is that you're trying to solve. Understand all the specifications of the problem that you're trying to solve. Understand what the constraints are, right? And then once you understand all of that, then you can start, seeing if you can find an abstract or a smaller version of it that could follow those assumptions. Alternatively, you can see, let's say, for the sorting problems or the traveling salesman problem, which are problems that have been solved already out there, you can find an algorithm that somebody else has come up with and use that algorithm, or look for something that you yourself have already solved and use that algorithm. But being able to think through a problem, and the truth is, when you're first starting out, I would strongly encourage you, even though there are sorting algorithms out there, think through for yourself, right, how you would go about solving the problem. And then once you come up with an idea, you can see, how long it potentially would take, right? How many times are you going through a loop? And then see if you can come up with a faster way of doing it, right? So just as a hint, for sorting algorithms, one way that's faster for doing it is potentially to split the pile into two piles and sort each individual pile. And it doesn't have to be two piles, it could be more than two piles, and then merge them back together. And that function makes things take a lot shorter in the long term. Okay, this is the end of this. I hope that this was helpful.